the I.O. request, so you can't pass it to the worker thread so that it knows what to do. So we take that thing, we pass it to the worker thread wakes up. When it's all done, it simply completes the I.O. request. The communication back to the file system driver from the worker thread is, these guys are all in the same address space. The thread can simply call back into the file system driver to do whatever it wants, because they're visible to each other. Okay, how do we handle buffering in all of these cases? Well, we have 3 different ways of handling buffers. We can either do what's called direct I.O. Direct I.O. simply says, I want you to take the data and put it from the device directly into the user's buffer. Or I want you to take the data directly out of the user buffer and DMA it out to the device. Okay? We do this in the case of some disk drivers that do DMA, or most disk drivers do DMA operations. What we do is we create something called an MDL, which is a memory descriptor list. We call the memory manager and we say, here's the address range that I want you to go lock down and build an MDL for. It goes and probes and locks all those pages into memory, all the physical pages, a memory descriptor list. Now I can take the memory descriptor list and hand it off to the HAL and the DMA programming code, and it can use the physical frame numbers, page frame numbers, PFNs, stored in the memory descriptor list. It uses that program to DMA, and boom, we tell the device, okay, go ahead and transfer, and it transferred directly into or out of the user's buffer. Another way to do that is to use an intermediary buffer. For operations where we're doing small I.O., you don't want to do this with really large I.O. Basically what happens is the user calls us and says, I want to transfer some data into this buffer from, say, a terminal. We don't want to take the user's buffer and lock it down, because the guy who's typing on the terminal may have gone to lunch, right? And we'd have all that buffer space locked down. So what we're going to do is we're going to allocate a small intermediary buffer and ask you, the driver, put the data in here, and when we're all done, we'll copy the data back into the user's address space. Not a big deal because we're doing small I.O. Same thing on the way out. We can write that way, for example, or printer drive. The parallel driver is an example of this. And then I didn't have a good word for, what do you call it if it's neither one, so I called it neither I.O. It's neither direct nor is it buffered. In this particular case, what I'm going to do is I'm going to probe all the buffers, but I'm not going to lock them down, and I'm not going to allocate an intermediary buffer. I'm going to defer the decision to do that to you. So I'm going to pass you the pointers to the user's buffers. They've already been probed. You know that you can touch them semi-safely. Note that because we're in a multi-processing environment, if I probe the user's argument, it says, I'm going to go to this address, and I probe it and say, okay, that address really is valid, and I pass it to you, between the time that I looked at it and the time that you go to touch it, another thread, or even the same thread, executing, could come along and delete the virtual address space that sits behind that address that I gave you. Now when you go to touch it, you're going to access violate. So you have to be very, very careful about how you touch those buffers. We'll talk about exception handlers and stuff like that, how you can wrap this stuff up just the same way that the kernel does and the executive does, so that all this stuff works really nicely. An example of this is a sound driver. A better example is every single one of our file system drivers uses this kind of I.O. And it's the way you determine which type of I.O. it is based on the device object. Okay, there are different kinds of drivers in terms of layering. We can layer device drivers here and file system drivers inside this I.O. system. What this allows you to do is it allows you to add value to the system by running a filter driver or by running a file system driver, et cetera, et cetera. You can plunk these things in the middle or on top of all the other drivers and then filter everything that goes through to those drivers, or capture things in the middle and change them, and et cetera, et cetera. One type of driver is what we call a monolithic driver. This is a driver that's given control by the I.O. system that works by itself to do absolutely everything that it needs to do to drive the device. An example of this would be a lathe driver. Obviously, a lathe doesn't need to have a file system driver sitting on top of it. You simply go out and program the lathe and say, here's what I want you to go do. If you'd like to layer the driver, then there are different kinds of layering that you can perform. We have something called a class port model. A class port model is where you have a driver that sits on top that drives a particular class of drivers, of devices. For example, disks, or tapes, or printers. All of these things can hang off of a SCSI bus. The SCSI bus adapter itself would be driven by another driver called a port driver. Okay? You could use the same analogy in a parallel port. You could have a network device and a disk hanging on a parallel port. Each one of those types of devices would be handled by a different class driver talking to the same port driver. Okay, and we'll talk about mini port drivers in a minute. The third way, and I don't recommend this, is to use thread-based device driver. Thread-based device drivers, we have one in the system. It's for the floppy driver, and this is for absolutely brain-dead devices. The floppy, I don't know if you've ever looked at the floppy driver, but this thing is really stupid. Okay, we talked a little bit earlier about our FIFO here. When someone wants to program the floppy driver to go perform a read or a write operation, the way this the way this device actually works is you give it a set of commands to tell it what to do. In the case of a read operation, you pass it 9 bytes, one at a time. When you pass it the first byte, it says, okay, I've got the first byte. When you go to pass it the second byte, you have to ask it, are you ready to take the next byte? And it's allowed to say, no. So you say, are you ready to take the next byte? No. Are you ready to take the next byte yet? No. This stupid thing can take up to 375 microseconds to say, okay, all right, fine, I'll take this stupid thing. If it does that for each of the 9 bytes, we've just eaten up over a time quantum for this thread. All right, so we don't want to do that. What we do instead is we take the IO request and we queue it to a thread that goes and asks the question, do you want this thing, or are you allowed to take this thing yet? And it simply sits there and asks about 10 times. If the stupid thing keeps saying no, it says, forget it. I'll actually go wait for a time quantum. It actually goes and waits for one time quantum, and it comes back, and now the answer is yes. But during that time, we weren't spinning, asking this device, wasting lots of processor time. We gave the processor time someone else who could actually use it. I said before that drivers could be layered. This allows to have intermediate drivers, to have drivers between 2 other drivers. Examples of those are the class driver, for example. It sits on top of a port driver and may sit underneath the file system driver. The file system talks to the disk driver, which talks to the SCSI driver. Other example is the stripe and mirroring drivers. The communication between all these drivers handled through something we call an IO stack location. Inside of an IRP is one stack location for every driver in the layer. Hello! Thank you. For all of you who are asleep. What we do is we have a stack location in each of the drivers so that you as the file system get a stack location and I tell you what operation we're performing. You then fill in the next stack location for the disk driver, for example, and tell it what operation you'd like to perform and simply call it. It then looks in its stack location to figure out what it's supposed to do and on and on. There's one of those per driver layer, and we are allowed to reuse the IRP. That is, you can program the disk underneath to perform a read operation, and when it's finished, you get back the IRP. You can now call it back and say, now I want to change it to a write, and go do a write. And you can continue to give the IO request packet back and forth between you and the device driver until you're all finished implementing the IO request, and then you can pass it back up to me, the IO system. Okay, so each stack location allows communication with the driver. What's in a stack location? Each stack location contains a major and minor function code that tells the next driver what it is you're trying to do. It contains a pointer to a file object, which is the open instantiation of that object that we're trying to perform on. The device object is the actual physical, virtual, or logical device that we're trying to perform the operation on. Some parameter flags, some parameters, and then some completion routine information that I use so that when the operation's finished, I can go back up the stack of all the layered drivers, call everyone, and notify them that the thing's finished. A diagram of what this looks like then is on the next slide. And as you can see, that there's a file system driver with a stack location, a fault-tolerant driver with a stack location, and a disk driver with a stack location. If the disk driver were implemented as a SCSI class and port driver, then there would be 2 stack locations there for that particular driver layer. Okay, so, and here, for example, is a SCSI class port driver model. What you see here is a disk class driver, a CD-ROM class driver, and a toaster class driver. Toaster in all of these presentations will represent some device that somebody has that we don't know about. Basically what happens, each one of those drivers is a layered device driver that talks to the port driver, and then the port driver talks to the hardware. You see something called a mini port driver here, the Wiz mini port driver and the XYZ mini port driver. Basically, you can have multiple types of ports in the system. For example, you might have a Adaptec and a future domain SCSI adapter on your system. Now, there's 2 different ways that you could write a port driver to handle that. One is, each one of those could be a separate port driver. Okay? What I was originally going to do was I was going to say, okay, here's what we'll do. I'll give you a template driver that handles all the interface between the class driver and your driver, handles all the I/O request packets, et cetera, and when you get done with all the dispatch routines and you're actually ready to go do something to the device, fill in this comment area, take the comments out, and fill in what you want to do to actually talk to your device. So what you do is you take this template driver and go fill in all the device-specific pieces in the driver. Okay, well, that would have worked. But then there would have been separate full-blown drivers for every single SCSI adapter that you had in the system. How about what we'll do is we'll take all the device-specific pieces of the driver and put those in another source module, and I'll call out to that piece. Okay, so when I have a command that I'd like to send out on the SCSI bus, when I get to the point where I have to do that, I simply call the mini port driver, and it contains the code to actually go send that command out, and when it's done, it returns. Okay, the mini port driver is that source module or source modules all compiled and linked as a separate driver. Okay, then the port driver becomes one DLL. There's only one in the system and everyone gets to use it. Okay, makes sense? Cool. Okay, so here's typical SCSI layering if you include the whole bit. Okay, here's the file systems. In the case of NTFS over here, toward the right or toward the middle, NTFS is now sitting on top of a mirror driver, which is then talking to the disk class driver, which is then talking to the port driver, which is doing call-outs to the mini ports. Okay? If we had a tape file system, what would happen is the I/O system would call the tape file system. The tape file system would pass it on to tape class driver. The tape class driver would call the mini port driver. The tape file system we have today is the raw tape file system. We have a raw file system for all mass storage devices that don't actually have a structure. So, for example, the way that you talk to an unformatted disk today is the I/O system. First operation that comes along for that particular device, we realize no file system has mounted this device. So what I do is I call all the active registered disk file systems in the system and say, go look at that device and tell me whether or not you recognize it, and if you do, mount it. If nobody recognizes it, then the raw file system says, okay, well, in that case, I recognize it, and now we get to talk to the disk through that file system driver. One of the advantages of always having a file system driver above these mass storage device drivers is we only have to do all the checking in one place. The disk drivers and the tape drivers don't have to check to see whether or not the thing that you gave it was in bounds. The file system already did that. It knows what it's doing. Okay? That works really nicely. It also makes all those little drivers, which we have lots of, considerably smaller. In the case of the network, we have something called the multiple UNC provider, also called the MUP. UNC stands for Universal Naming Convention. That's the //. Basically what happens is the first time that we see a backslash in the API at the Win32 level, we take that and we translate that name into the MUP driver, and we call the MUP driver. The MUP driver takes the slash off and calls all the redirectors and requesters in the system and says, do you understand this name? One of them comes back, hopefully, and says, yes, I understand this name. Now what happens is it says, okay, great, I'll get out of the way and we'll resubmit this request directly to you. Now, the user application is talking directly to the network redirector or requester for the type of network that that request was supposed to go to. Okay, and then MUP gets out of the way. Okay, this is a lot like what some of your filter drivers are going to look like. Okay, those requesters and redirectors then talk TDI, the transport driver interface that Dave was talking about this morning, and TDI then talks to the NDIS drivers, and the NDIS drivers talk to, again, the mini port drivers for NDIS. Okay, NDIS is a network driver interface specification. We've done the same kind of thing there that we did in the mini port in the SCSI. Okay, so there are different types of scenarios that you can use to talk about layering in the system. And device naming is an important key for this, and I'll talk about that as we go along. The types of layering that you could have is you could have a very simple driver, like a lathe driver. You can actually come along and layer a driver on top of that lathe driver. However, anytime you layer a driver on top of another driver, remember, you have to be able to implement all of the same interfaces that the driver underneath you implemented. Okay? Does that make sense? So in other words, if it has a device I/O control so they can control what lathe is doing, you can't say, well, I'm not going to do a device I/O control because I call your driver first, and I'm going to find the entry point that says this is an invalid device request, and the lathe will never get the request. Okay? A second type is mass storage devices, then intermediate drivers or filter drivers inside of other stacks of drivers, network device drivers, and then what I call a file system filter driver, which is, and this is the type of driver that filters all requests to all file systems. Okay, you may, as we go through here, may want to put an X or a check mark in the red device drivers, or in this particular case, it's the filter driver. So normally what would happen is the I/O request would come in to the single layered device driver called the lathe device object. Okay? So the I/O system would simply talk directly to that particular device driver. You, however, can attach yourself to that driver using I/O attached device, and now you can get all of the requests that are supposed to go to that device driver. You can get those requests before it goes to it. Okay? So you get the request. It now has two stack locations. One for you, that was the description of the original request, and one for the lathe driver, which you get to fill in to tell the lathe driver what to do. Okay? Makes sense? Pretty simple. File system device drivers for mass storage devices sit on top of disk device objects or tape device objects, etc., in much the same way, except that you don't use I/O attached device. For mass storage devices, we have a small problem. If you ask the question, what's the difference between the naming convention for a device, like a disk, versus what's the naming convention for a network device, they're very different from each other. In the case of a disk, you're going to give me the name of the physical device that you want to talk to at the API level. For example, C:. C: says, I want to talk to that particular disk partition. Correct? Okay. Somehow what I have to do then in the I/O system is I have to figure out what set of drivers do I need to go through first before I call that disk driver. For example, if you open a directory, a handle to a directory, we can't call the AT disk driver and say, we'd like to query this directory. We can't do that. We have to go to a file system first. So what happens is the name of the device gets you to the bottom of the stack. The thing on the right there called a VPB is a volume parameter block. The volume parameter block is the data structure that I use to figure out where the top of the driver stack is that I need to get to so that I can get back down here. Okay, so we started with the name of the device on the bottom, and this takes us up to the top. Okay, so that's how your file system device driver is going to get called. I said before that when the first time that I go to call this device object, device driver, I'm going to ask the question, was this thing mounted? Well, the volume parameter block is the thing that tells me whether or not this device has been mounted. If there is VPB, then it means that there's got to be a file system sitting on top of it. If it hasn't been mounted, then I'm going to go through all of the registered active file systems in the system, call them and tell them, here's a pointer to this device object. Go out and see whether or not this is something you understand. Okay? How do you make your file system an active registered file system? Well, there's an API called IO registered file system. And you call that, and now you're in a list of all the other file systems in the system that I'm going to call. LIFO. Okay? So I'm going to call each one of you until one of you says OK. When you say OK, I understand this particular on disk structure. The way you represent that to me is you create a device object called a volume device, and that's what we have here. This is the file system volume device object. And you fill in a pointer in the VPB that points to that. Okay? Now what I know is I know where your particular volume device object is, and I hand the request to you from now on for that particular device. Okay? And then you pass it along to the disk device driver if you need to. Okay, so how about an intermediate driver? Here's a filter driver device object that's inserted itself in between the disk driver and the file system driver. Note that this guy had to be there before the file system ever touched that disk. Why? Because once I've told you, the file system, it's a pointer to a device object that I want you to mount, you now have stored in your device object the pointer to the device object for the driver that you're talking to. Once you fill that in, no one can come along and insert something in between it. Okay? So if this filter driver that was sitting in the middle of here were a fault-tolerant driver, for example, that fault-tolerant driver needs to get loaded after all the disk drivers, but before we actually go to touch any of the disks. Well, that's a pretty simple thing to do, and we'll show you how to do that. Now what happens is when the IO request comes in, it still says C:. Actually, it doesn't say C: by the time it gets to me, but let's pretend for the simplicity today that it does. At any rate, it's going to point me directly to that disk device object. When I go out and I have to see whether there's a VPP pointer, I say, yes, there is. No, it hasn't been mounted. I need to put together a request to you, the file system driver, for each one of the registered active file systems, and call you and say, mount this thing. However, when I say mount this thing, I'm going to give you a pointer to the filter driver's device object, not the real device object. So now, as far as you're concerned, you're talking to the filter driver, but it looks to you just a physical device. Okay, and there's really no way to tell the difference unless you go poking around in the VPB, because as you can see, the VPB also contains a pointer back to the real device object for this device. Okay, networks we already talked about. The reason that networks are important is because now, what do you give it for a name? When you go to open a network device, you don't say, I want you to go to the Youngerman Bass card number 3 to go talk to the network, right? You give it the name of some server somewhere. What that does is parse this all the way at the top, and we work our way down from there, right? In the case of physical mass storage devices, we started at the bottom. We had to somehow get ourselves up to the top and work our way back down, okay? And so that's the difference. There's no VPBs associated with network devices because we started with the name at the top. Okay, and then finally, we have filter drivers that sit on top of file system drivers. Okay, in this particular case, what's going on is the first operation for the disk comes along, sees that the disk has not been mounted, and it calls the registered active file system. The registered active file system is going to go mount it. But before the registered active file system gets the request, there's another file system filter driver sitting on top of it that it gets to see before file system gets to see it. Now what you can do is you can say C:, well, that's really this guy over here, not that guy over there. Okay? And you get to do that before the file system even gets to see it. Okay? So this is how you sit yourself on top of all of the drivers, all file system drivers, so that you can capture all the opens to all of those guys. Okay, so let's talk about what's a file system actually look like. The components of a file system driver are, very quickly, there's an initialization routine. The initialization routine in a file system driver creates a single device object that it registers as the active registered file system. Fills in the driver object with all your entry points and returns and says, I'm done. That's all you got to do. It has dispatch routines. The dispatch routines are the routines that I call when you get called via IO call driver for each of the functions that you perform, such as read, write, etc., etc. You need to fill those in the driver object. That's part of what you did during initialization routine. And you can fill them in such that you have one separate routine for every major function code, or you can mix and match them. You can do whatever you like. Fast IO routines. If you'd like to use the fast IO path, then then what you do is you allocate and initialize a table of functions to dispatch routines, and you put a pointer to that in the driver object. Now what happens is I come in and I call you directly. There are APIs in the system that we use today in our file systems that you can use to implement some of these kinds of functions. For example, everybody can use a file system runtime library routine to do read operations using FastPath. The way you do that is your internal data structure has a header on it that's common. If you do it that way, then what happens is you don't have to write the read path for your device at all. Why? Because the fast IO path interacts with the memory manager and the cache manager to take already cached data and put that in the user's buffer when the user requested a read. If there's a miss and we don't have the read data, then we take a fault and we go around the IO request packet method and come back in your driver via the IO request method. Okay? In that case, what that means is you never even have to get involved. Your file system never even has to get involved if the data is in the cache. Okay? I know that's a little fuzzy right now. Everyone's looking at me with glassy eyes, or maybe I'm just being really boring. But we'll talk about that some more. Completion routines are the part of your driver that get called when you pass down an IO request packet to someone below you. You might like to know when it's finished. Okay? The completion routines are the routines that the IO system calls as the IO request is being completed back up the stack of drivers. Okay? So you're going to set the rest of a completion routine for an IO request, and I'm going to call that completion routine when the IO packet is complete. Worker thread routines are routines that you can execute as part of your file system in the context of a work thread, that is, in the context of another thread. And error log routines are routines that you can optionally add to perform error logging. Okay, so what happens when we pass an IO request? How does IO request processing actually happen? Well, let's take the case of a Windows application. A Windows application calls the Win32 API, which then calls the Windows NT system service, and the system service checks parameters, checks to make sure that you can perform that particular operation on that particular device, and then generates an IO request packet. The IO request packet is passed in via IO call driver. I call your driver the same way another driver calls your driver via IO call driver. I call you at your driver dispatch routine. The processing in the highest level driver processes that IO request packet and optionally passes it down to another one. Eventually, we're going to make it down to some device driver that's actually going to start this IO operation if we needed to. That is, the data wasn't our cache. If we need to actually start it, then we're going to call the start IO routine inside the device driver. Device driver is going to synchronize execution with the interrupt service routine so that it can actually program the device to go perform the operation, and then it's going to return. We're going to return all the way back up through the stack of drivers, and the I/O system is either going to return back to the application if it was an asynchronous operation, or it's going to wait for the operation to complete if it was synchronous. Eventually, someday, the device is going to interrupt, and we're going to call the interrupt service routine for the device driver, which is going to, again, gather some minimal state, make the thing stop interrupting, and queue a DPC. At some point in the future, the DPC routine will be called at a lower IRQL than the interrupt service routine was called, so that we're not blocking any other device interrupts. And that thing is going to finish up the processing of this particular operation. It's going to start the next operation on that device, if there is one, and then tell the I/O system, okay, we're finished with this I/O request. By telling the I/O system that we're finished, the I/O system is now going to call all the drivers back up the stack of drivers, let everyone know that this thing's complete, and when it's all finished, it is going to queue an APC back to the original requesting thread so that I can get in its context and copy the data and the status and set its events to the signaled state or whatever I need to do. Okay. And that's about all there is to processing one. Right. That's like, yeah, right. Okay. So, file systems. File system support, we do support active, multiple, registered file systems in the system all at the same time. The last one in the list of active registered guys will always be the raw file system. That way it can handle devices that we don't recognize. File systems are loadable just like any other device driver, but they're not necessarily unloadable. You can make your driver unloadable if you can figure out how to do it. We support automatic volume mounting and verification. That's part of the stuff that I was talking about before. When you come out to a device and you go look at it for the first time, we find out that it's never been mounted. We go through that list of file systems. All the file systems today, straight out of the box, use a single global cache manager. It's a very nice cache manager. We suggest that you use it. It keeps all of the files in the system coherent. Cache manager can use up to all of available physical memory to cache files. It's pretty neat. And then there are these common structures that I talk about that are supported by the FSRTL. That's the File System Runtime Library. I said if you use these common headers, then you can use File System Runtime Library routines to perform some of the functions you would need to perform in your file system driver, and you just use those instead of having to reinvent the wheel. File systems that we support today, this is a partial list, are FAT, HPFS, NTFS, CDFS, namepipe file system, slot file system, the LAN manager redirector, and the network requester. Okay, as I said before, the cache manager supports a single global cache manager for all the file systems. Cache can expand to all of physical memory. That is, if applications aren't needing the memory for something else, right. When have you ever seen an application that didn't use every bit that it could get, right? If they're not using it, we use it. If they need it, we give some of it up. Okay, and we continue to give it up until we reach a really nice balance. Yeah, right. The memory, otherwise commonly known as, what are we going to do? We're going to use all of the memory that we possibly use. The memory manager works with the cache manager to use the working set concept, which Lou will talk about tomorrow, to manage the cache. That is, what's in the cache and what's not, what's in a user's application address space that it can actually touch and not have fault in from elsewhere, such as the paging file or the free page list or the modified page list. That's called the working set. And we do maintain a coherency between map files and read-write. That is, if you're an application and you map a file, if someone else has that file open, while you're poking around in your memory, another process can read and write to and from the file via NT read file and NT write file. The system services today, we just to go do that. They can be doing that at the same time that you're looking at your memory, and when we actually write something into the file, it actually appears in your virtual address space. Okay? Two people can use the same file, map it in different places in their address space, and share it that way and maintain a coherency between those. Okay, part of the I/O system today is fault-tolerant driver. We support volume sets, we support striping, and we support striping with parity. That's RAID 0 and RAID 5. We support uninterruptible power supplies, and we support mirroring. Okay, is everyone familiar with those concepts? Volume sets and mirroring and logical volume sets? Okay, great, super. Okay, wow, this is great. The summary page. Okay, so in summary, drivers are portable. They're written to follow a set of guidelines and a set of rules such that your driver will work on other platforms, such that your driver will work when we add processors to the system, et cetera, et cetera. And we have literally taken our file systems and we ported them to a new architecture. We simply recompiled them, relinked them, and they ran first time, right out of the box. It really does work, folks. They're secure. We support ACLs. We have security. We can do. We have a C2. We're working on a C2 certification. We're really close. We're multi-user, multi-threaded, multi-processor. All those wonderful terms. We can layer drivers. We're object-oriented. We have device objects and driver objects, all these wonderful things that you can use. And it's pretty darn fast. Okay. Questions while I still have a voice. And I'm not going to drag this out. I'm going to take like 4 or 5 questions publicly, and then you can all come and bombard me throughout the rest of the day. Yes, sir.
Position above the file systems. How did that actually get hooked into the I/O manager so that it was being called 4 file systems? Just the same attached concept? Or?
Yeah, basically, okay, the question was, in the diagram where I had a filter driver sitting on top of the file system drivers, how did that thing actually get into picture? The answer is, what happens is, I said that when a file system loads, it's going to create a device object that's going to register as an active registered file system in the system. What you do as a filter driver is you create a device object and attach it to that. Okay? Now, every time it gets a request, you get to see what kind of request it got. It gets a mount request. If the mount request succeeds, by definition, what the file system underneath you has done is it is created a volume device object, which is pointed to by the VPB, and that means it's mounted. What you do is create another device object and set it on top of the volume device object. Excuse me. Now you can watch all the requests that not only to the file system, but to all the volumes that that file system is actually servicing. Yes, sir.
In the area of fault tolerance, what does what you guys think in terms of NT for CPU or server buildings? How do you, like, I want to have 2 NT systems talk to each other and have a file system be responsible for them?
Okay, the question was, in terms of fault tolerance, what are we going to do in the future to handle the case where I have 2 systems handling the same device and fail over from one to the other? That is beyond the scope of anything I will say in this entire conference. Yes, sir.
Does the I/O subsystem serialize requests on a per handle basis or per process basis or a combination?
Okay, the question is, does the I/O system serialize I/O requests on a per handle basis, per process basis, or per thread basis? Is that what your question was?
Yeah.
Okay. The answer to that question is, it depends on how the file was opened. First of all, there is no serialization of I/O requests to the same file via different file lines. If you open the file twice, there's no serialization. If, however, within the context of a process or a thread, you open a file and you say that you would like to have all I/O operations performed on that file through that file object be synchronous I/O, then all operations that you perform on that file object, be it through that thread, through that process, or through a sub-process that inherits that handle, all of those things will not only be synchronized, they will be serialized. Okay? So what that allows us to do is it allows a thread to say, I would like to read position X. Once we've read from position X and the I/O operation has been completed, we will update X by X plus the number of bytes read so that the next operation performed on that file will be read or written from position Y. Okay. Therefore, the next I/O operation that be performed on that particular file object will be performed at position Y unless someone changes it. Yes, sir.
I was under the impression that the HPFS file system was going to be included in the developer kit, but it apparently is going to be the CDFS instead. And I was wondering where I can go to get examples of how to implement mirroring or striping.
Okay, the question was, he was under the impression that the HPFS file system sources were going to be in the kit, and now he found out CDFS was. And his question is, if he doesn't have the HPFS sources, how does he go out and figure out, how does he go look for examples of how to do mirroring? Our HPFS file system is just a file system. It doesn't do any mirroring. Our fault-tolerant driver is the guy that does the mirroring.
Well, you just showed a graphic back here that showed it over a layer. Yeah.
That was an example.
Like
Yes, right. Okay, so this point was in the diagram of file system, mass storage file systems sitting on top of file systems sitting on top of devices. We had an example where we had HPFS sitting on top of I think it was a stripe driver. Right? Right. That driver could be anything. It could be striping, it could be mirroring, it could be anything. As far as you, the file system writer, are concerned, if you're writing a file system, what's below you could be a mirror or a disk or a stripe. I don't think we have any examples of how to actually do that, but it's pretty simple. I mean, basically what happens is you're an intermediate driver, not a file system driver. You attach yourself to the disks via I/O attached device. Now what happens is you get to look at all the requests that come down from file systems. It didn't make any difference whether it's FAT or HPFS or NTFS or any file systems. They just see, all the file system sees is one long contiguous file of bytes, right? You, the fault-tolerant driver, if you want to write a mirror driver, simply generate one device object that represented two or more of these guys that you're mirroring underneath you. The file system would count you, then you would take the requests that come in and divvy them up, right? It's that simple.
But there's a mirror driver in, like NTFS uses one, right? I mean,
NTFS doesn't use a mirror driver. NT has a separate driver called a mirror driver, right?
The API is public or available.
The APIs are just like, it's just a driver. It's I/O call driver, right? All the intermediate drivers and filter drivers, file system drivers, device drivers, they all look the same, right? It's I/O call driver. You pass me a pointer to a device object and an I/O request packet. I take function code out of the request packet, index into the driver, and that's the dispatch routine, whether it's read or write or whatever. So if your file system is being mirrored, what do you care? If you're the mirror system, you have to figure out how to take one device object and take a single device request packet that you got, send it to a bunch of different mirrors. Pretty simple. You call IO allocate IRP, fill it in, pass one of them to one and one of them to the other, and you're done. Okay.
Our system implements a user mode virtual memory by using virtual alloc and caching.
Next question. No.
What happens is that all of that works fine as long as the users are using ordinary instructions to modify memory. But when they pass a location to this magic memory to an I/O device, the I/O device says, wait a minute, there's no page there, you can't write it. We'd like to be able to fault on those pages and make them real before the I/O access.
Okay, this question is basically, we have a situation where we're implementing a version of memory management inside of a user process, and I'll take your question offline because it's not so straightforward.
So the whole file model works in the way, say, for some services that we'd like to implement in the kernel, say, create client and server ports or object proxies for distributed object systems. And you ran into it with sockets, for example, and had to create an AFD. So where does take ports, for example, if you wanted to do NetIPC, where does that fit in your model?
Okay, I'm not sure if this is, okay. Let's start by stating the statement, which was, what we'd like to do is something other than what you can do in a file system, and the file system keep getting in our way. We'd like to be able to do something like generate our own OPC ports. Windows NT today does not allow kernel extensions. It allows file system extensions. Everything that you add is within the model of the I/O system. At some point in the future, we will give you a way of extending the kernel outside of the file system interface and the device driver interface outside of the I/O system. We haven't done that yet because it's very complicated to do and get right. Okay, so we'll do that at some point in the future.
How do you index the global cache, and how do you prevent or avoid aliasing?
Okay, the question was, how do you index into the global cache?
Yeah, for instance, suppose I read...
How about if I answer the question without you expounding first, and then if I don't answer it right, you can expound some more.
Okay.
The answer is the cache manager uses the same file object that you use to describe the file. When someone wants to read or write the file, they're going to give you a byte offset position within that file. Okay? The cache manager is the only person that knows where in virtual memory that actually is and whether or not it's in virtual memory and the memory manager. From the file system's point of view, you don't care. There is no set number of pages somewhere in memory that we use for this stuff. There is no index into a bunch of blocks. It's just a bunch of virtual memory address space.
I understand, but really the full question is, suppose...
If you have more, let's take it off, okay?
Okay, all right.
Yeah. This is the last question.
Sure. By not providing a file system that includes a write path, it will be so much more difficult for people to implement correctly creation of directories and creation of files. CDFS will only show us the read path for us, which is less than half of the FSD.
Okay, valid point. His point was, if you only gave us CDFS, then you only showed us how to do a read. You didn't show us how to do a write. I mean, creating a file from the I/O system's point of view is, I create the file object. All you have to do is create the thing on the disk that backs it up. I'm going to pass you the same pointers for a write that I am for read. It's just a question of which way the direction of the data is going.
I meant more on setting protection, creating directory structures, all the other things that we change.
Okay, so he's pointing out that I haven't shown you how to create a directory structure. I haven't shown you how to set protection. Creating directory structure is something that is file system specific. I have nothing to do with it. The directory control blocks in... Sorry.
I meant how we get called. Sample code that responds appropriately to the call.
Oh, example of how you get called. I mean, it's the same API. It's just a different bit that's set that says we're creating a directory, not file. Right? I mean, from the file system's point of view, you need to have your own directory hierarchy structure of what you have. It's straightforward to me. We can talk about it some more. I don't know what I can give you fat, but no, these guys are all shaking their head going no. Okay, let's I'd like to take all the rest of the questions offline. I'm going hoarse and I don't feel very well. So thank you very much.
Thank you, Darryl. We're a couple of minutes early for lunch, but I think they've either got it out there or it's very close to being out there. Since we oversold the conference pretty much, we'd like to start people starting eating on the round tables and then progress out to wherever you can find. You can sit here at these tables if you want to eat. There's also some space outside, and the weather actually looks like it's clearing up enough that it might actually be okay to sit out there if you don't mind being a little cold. The view's nice. So we'll go ahead and break for lunch. We start back in here at 1:30.